So the first bifurcation was transient versus steady state analysis. And for transient analysis, it was actually fairly straightforward. You're just going to, you start the simulation up, you run it, and you just keep doing that independently, and you're basically there. As we've seen, when it comes to steady state, though, there are two significant issues we have to deal with. The first is initialization bias, and the second is autocorrelation. We've seen one approach to mitigating that, and that's the replication deletion approach. And that's the most straightforward. It's the easiest to explain. It's the easiest to justify. Basically, to mitigate initialization bias, you have the warm-up period. And once the simulation quote is warmed up, meaning it's reached steady state, then you truncate, you delete all that data, and then you continue collecting. And then you repeat that whole process again and again. And again, that method is the most straightforward. It's the easiest to explain. It's the easiest to justify. But one of the issues with that is that it can be, you can look at it as being very wasteful. In other words, that replicate, all that deletion stuff that goes on, every time you replicate it, it's like you run the thing to steady state, then you throw away all the stuff that took you there. And as you saw, sometimes it takes a lot of observations in order to reach steady state. Like for our simple queue, I think it was around 10,000 or so delays in queue it took before it looked like the system was settling down. And so each replication would throw away all those data. And so a while back, some smart guy said, well, once we're in steady state, is there anything that we can do to just kind of, instead of just doing this again and again and throwing out all those initial observations, is there any way that once we're in steady state, can we actually get something of an estimate of the variance that's kind of good enough? Again, the issue is the estimate of the variance, not the estimate of the mean. I mean, obviously, the more observations that go into the estimate of the mean, the better it's going to be, even with autocorrelation. But the autocorrelation is what we're stuck on here. Even once we reach steady state, there is autocorrelation, and as we saw last time, that autocorrelation can be significant. And what that does is that makes our estimate of the variance problematic. That is, the normal estimate of the variance is not acceptable. But they noticed that if you collect, basically, if you kind of collect batches of data in steady state, then, and actually you can, under mild assumptions, you can kind of show this, that as the batch size gets bigger and bigger, the correlation between the batches actually goes to zero as the batches get big enough. So in other words, if we can take these batches where once we're in steady state, we're just going to have one long run instead of just repeating things and throwing away data. We have one long run, and what we're going to do is we're going to collect data in batches, and then take the mean of the batches. So each batch and it's called the method of batch means. So each batch is going to produce the mean of the raw data. So again, we're not going to go right to the raw data. We're going to look in batches. So again, under mild assumptions, again, mild meaning, we have to make certain assumptions about the structure of the correlation or whatever. There's a bunch of math involved that I'm not going to bore you with. But once we reach a certain correlation between the batches, if that's small enough, then we can treat these batch means as if they were IID, and thereby get an estimate of the variance and thereby create our confidence interval. Again, why do this? Because we're not wasting all the stuff we're throwing away. So mathematically, it looks something like this. So if we were, these X's are the, these would be the raw data. Now I'm just going to do this for tally data. We can do all this for time varying data, and this time we're not. Okay, so these X's, we can think of these as successive delays in queue, or time in system, or again, whatever measure you're interested in. So as before, we still have the problem of initialization bias. And so we have this transient period where these are all just to warm up the system. And we're still going to throw all these away. But then once if we've chosen our truncation point well enough so that we are actually more or less in steady state, then going forward, we're going to say, if our batch size is B, then I'm going to take, say, the first B observations after steady state and combine those to get one mean. So this is 1. And then I'll take the next B guys and take those averages, and that'll be the second observation. All the way up to my nth observation is going to be, again, the mean of the last B observations that we have. So the total number that we're going to run is going to be our transient plus N, which are the number of batches. So N is the number of batches. And so the transient observations plus the number of batches times the batch size, that's how many total observations that we'll need. Now, this you need to be a little bit careful with this, and when I demonstrate it, I'll kind of show you what some of that's about. And again, this is for the mathematically inclined. You don't have to worry about that. In days of yore, I would kind of torture students with kind of trying to unravel the math, but that's not really what's going on. Okay, so the idea now is that we have these, we have these N observations, which themselves are means. So we now have N of these guys. And each one is the mean of these batches. And again, if we've taken our batches big enough, these are approximately uncorrelated. And so to form our estimate, we take our grand mean, that is the mean of the means. So we see that X double bar is just the mean of the X bars, and there are N of those because we have N batches. And our estimate of the variance is just the normal estimate of the variance, of the sample variance. So each observation minus its mean squared. Actually, I'm sorry, the difference between the mean and the observation squared and add them up. Okay, that's the normal. And then we are now assuming that our batch sizes are big enough so that the correlation is small. Now our approximate confidence interval is, our estimate is the grand mean, the mean of the means, the variance, or the standard deviation, which is the square of the variance. We have N observations now, N batches. So we have N minus 1 degrees of freedom. and then we divide by the square root of n. So this is just the normal confidence interval equation using the mean of the means, using the grand mean and the variance of the means, of the batch means. Okay, so basically now we have several issues. Well, first, choosing a truncation point. If we're doing steady state analysis, choosing the truncation point is always going to be an issue, because regardless of how you squirm, the initial bias is always going to be there. And then the second issue is we need to choose our batch size. So again, the batch size, it needs to be large enough for the batches to be approximately uncorrelated. That's something that you can actually play with. I'm not going to do that here, but what I'll do is I'll kind of show you the impact of some of the of changing the batch size when I look at the. Okay, so let's see. I've already. Okay, I did this last time. This was just in case I didn't get to it. So we're not going to do that. I've done that already. We've shown the autocorrelation. And okay, so now I want to show you how to use the batch means. So, and again, this has been pushed to Git. So there's a class there, batch means confidence interval tally. That's again, I'm only going to do it for a tally. We can do it for time varying. Okay, so here I've chosen 500 batches and a batch size of 10,000 and a truncation point of 10,000. This is the same, again, I'm using the same entity server queue as before. And we've already seen that the truncation point of 10,000 is a reasonable one. So we're gonna punt on that. So we need to choose how many batches and what the batch size is. And remember that based on our previous analysis, we've seen that the steady state expected delay in the queue was around 35 or so. Remember that. So I chose a batch size here of 10,000. Why? Because in just doing some initial experiments, it turned out that you needed a fairly hefty batch size in order to have approximately uncorrelated stuff. But so, here's the thing: is that even the mean can be can be way off if your batch size is too small. So, for example, supposing we have a batch size of 50. So, well, so we'll come back to that. Let me just walk you through what we have here. Everything is the same as before, except for this. Now, our inner stat is a class in SimKit called batch means tally stat. And we set it up just the same as before, except it's got two it's got three arguments in its constructor. Okay, first is the name of the state. So we're still looking at delay in queue. The second argument is the truncation point. So this assumes that we will be needing a truncation point. So we're going to give that. And then finally, the batch size. So under the hood, what this class is doing is it's collecting data until the truncation point. When it reaches the truncation point, it throws it away. And then from then on, it starts collecting things in batches. So as it collects stuff, it kind of puts them in a temporary area. And then when a batch gets complete, it then passes it to the actual stat. So if we get the count, that'll be the number of batches. If we get the mean, that's the mean of the batches. And if we get the standard deviation, that's the standard deviation of the batches for this class. And again, now instead of having a do loop, we're just going to have one single long replication. Okay, so now, and then we're going to form our confidence interval based upon the based upon this one delay in queue batch mean stat, which is one of these batch means tally objects. So again, the half width is the standard deviation times the quantile over the square root, and then the mean is going to be our estimate of it. So now, remember I said that the batch size that I landed on was about 10,000, but let's just see, just with this, let's see what happens if we have a smaller batch size. In this case, we kind of know what the answer is. So we see that if I only have a batch size of 50, then my estimate is way low. Okay, remember we know that the steady state mean should be around 35. So if I bump it up to 100 and run it again, so look, it's fluctuated, it actually went down. So what if I bump the batch size up to 500? And it takes a little longer. Okay, so now I've kind of overshot it a little bit in the other direction. So even at 1,000, okay, it's still kind of going high. But whereas if now this is going to take a little while longer. If I run it for the batch size of 10,000 that I eventually landed on, we will see that after a little bit of time, we wind up with a kind of a more accurate, 34, high 34, that's again, plus or minus about 3. So how can I make this tighter? I could make it tighter by increasing the number of batches. So if I say bump this up to 1,000 batches, it'll take about twice as long, but hopefully come in with a tighter confidence interval. Okay, so and while this is grinding away, then, and speaking of the size of the confidence interval, we can apply the sequential method to this very same thing. Now, it takes a little, in this particular case, the classes in SimKit are not completely ready for this, so we actually had to write a special class, as we'll see. Okay, so we see now that we have a slightly tighter confidence interval. Again, now we're definitely honing in on what we had peaked to be the answer. And so this is the method of batch means. So again, what are the levers that you have? In this case, we have the size of the batch. Again, you want to make that to the point where the batches are roughly uncorrelated. And then the number of batches, just as with the number of replications, as we saw for the more brute force method, that's pretty much our only lever to get our confidence interval tighter. But having said that, we can apply a sequential method. So the whole thing, that sequential method is applicable regardless of what the situation is. Okay, so the other class called batch means sequential tally. Again, it's still a tally, same model as before. It's our multiple server queue with the same parameters as we had. Only now I'm going to say my desired half width is 2. So here I got it down to like 2.05 something. And so how do I do that? Well, everything else is kind of more or less the same. As I have a batch size, a truncation point, but now instead of specifying the number of batches, I'm specifying the desired half width. So in other words, just as before, where the heck was it? again, I still have a long simulation run, but I need to be periodically kind of checking in to see what is going on. So for that, I have something called a batch means helper. And I just because I wrote it as an inner class, because you can do that. I could have written this as a separate class, but you know. Okay, so in the batch means helper is our batch means tally stat. And I'm going to tell it the desired half width and the alpha, and that's all going to be in the constructor here. And it's a property change listener. So here's how to, you know, it's not a lot of code, but you just have to be a little careful. So first of all, it has a name, and that's the property it's going to listen to. So I want this just to listen and deal with the same property that our batch means tally stat is listening to. And how do I know that? I know that from the property change event has a method called get property name. And the property name is the name of the property. Duh. Where does it get that from? Well, remember when we fire a property change in our component, the first argument is a string that's typically the name of the state. That's where that is what the property name is. And so this says, if I hear a property change event and it's equal to the name of the property change, the property that my batch means tally stat is interested in, then I will, first what I'll do is I'm gonna just pass that property change event to the batch means tally stat. And then now here I say, well, okay, I always want to have at least 30 observations. That's to prevent early termination. And then this is just kind of a brute force way of doing it, but there are cleverer ways, but I wasn't feeling terribly clever. So each time this happens, I'm gonna compute my quantile based upon the count. And then I'm going to compute my half width, again, from the batch means tally stat. And then now I just have a plain old if statement. So if my half width is less than my desired half width, then I'm going to just stop the simulation. So we haven't made this call before, but if you think about it, if you can start a simulation, you can stop a simulation. And this is how we stop a simulation. Okay, so if we run that, then now probably this, just to give a periodic report on how we're doing. Oh yeah, no, I remember why I didn't do that. Because see what happens is, okay, so it only took 43 seconds. So now look, notice it needed about 100, a little over 1,000 batches in order to get less than 2. And again, we can always play with this. So let's say if I wanted something even less, like 1.8, then yeah, the tricky thing here is that each property change is a result of, in this case, a new delay in queue. But the new delay in, it would just take a little bit of more code to, because let's say if I have a batch size of 10,000 as I have here, then I'm going to get 10,000 on the first batch, and then 10,000 on the second batch, and then I don't really want that. So, so we'll just kind of be looking at the blinking cursor for just a little bit. But you see what the idea here is, that you have, again, just to go back to the beginning, two choices: terminating or steady state. If it's terminating, again, it's just very straightforward. You just run it independently and end of story. If it's steady state, then you have to worry about initialization bias, meaning finding a truncation. And then you have to worry about autocorrelation. We've seen two ways of then proceeding once we have a truncation point and dealing with autocorrelation. The first is the replication deletion. The downside of that is that we're wasting a lot of cycles on data that we know we're going to throw away. The second batch means approach says, okay, once we've reached steady state, if I start collecting things in batches, and I can just kind of keep running, and I don't have to throw away anything, you know, any additional things beyond one truncation point worth of stuff. And then for all of that, then there's another dimension, if you will, which is, are we going to run it in with a fixed sample size or sequentially? The advantage of a fixed sample size is that it's very straightforward. You say, I'm going to run it for this many replications, and then boom. The downside of that is that we don't have control over the size of our half-width. And whatever the size of the half-width comes out of a fixed sample size run is what it is. We're stuck with it. The advantage of using a sequential method is that now we can say, I want my half-width to be less than or equal to some value. Meaning that I want to, here I'm confident, I'm 99% confident that my true mean is within 1.8 or so of this value. And again, remember that confidence doesn't mean that it's not the same as probability. What this means is that I have performed an experiment that has a 99% chance of working, of being correct. What is correct? Correct is if the actual expected delay in Q is in this confidence interval. That would be correct. And what the confidence means, and you've hopefully heard this in your statistics classes as well, is that if I were to perform this same experiment, let's say 100 times, then on average, one time out of the 99, it's actually going to miss. Or to put a positive spin, 99 times out of 100, my true but unknown mean is going to be within this computed confidence interval. So that's what gives me confidence. In other words, I've made what I think to be a very good bet. I've made a bet with a 0.99 chance of success. I don't know what the outcome is, because I still don't know what the actual delay, expected delay in Q is in steady state here. I'll never know that. But what I have done is I've made a bet with a 0.99 chance of being correct, and I'm declaring victory. So just as with the, so the disadvantage is that it may take a real long time to get to where I want to go. So let's say if my desired half-width is 1, now to be honest, I'm not sure how long it's going to take. I may run out of things to say before this thing ends. before it winds up. So the downside is that this could run for a very long time, because remember, the half width decreases at a rate of 1 over the square root of n, and that's actually pretty slow. It's less than linear. So the advantage of a fixed size experiment is that I know when it's going to end. And on the other hand, again, my confidence interval could be too big. So here, baked into the sequential method is the fact that my confidence interval is at the end, once it comes out, is going to be within my pre-specified limit.